Okay, for this video, I'll be going through pure physics magnetism chapter. Okay, so let's look at the first success criteria. Now, state the properties of magnet. Okay, so magnets attract magnetic material. Okay, not all things are magnet and not all things are magnetic materials. Okay, the list of magnetic materials in our syllabus will be iron, okay, steel, which is an alloy, nickel, and cobalt. Okay, with the first two most commonly mentioned in our syllabus, iron and steel. Later on, we'll make a distinction between the both of them. Now, magnets have two poles. It's always occurring in pairs, and magnetic effect is strongest at the poles. Point number 3, a freely suspended magnet comes to rest in a north-south direction towards Earth's magnetic poles. Okay, so basically Earth is like a magnet. So that's how people find their way using a compass, right? Inside the compass, there's actually a magnet. Okay, so sometimes the compass may be drawn like that. Sometimes the compass is drawn like that with this part in red in color. Okay, so the arrow, it is the North Pole, right? Inside the compass, there is actually magnets. Okay, so the tip of the arrow is actually a North Pole. That means the end of the arrow is a South Pole. Similarly, the colored red colored part is a North Pole, and the other part will be a South Pole. Okay, so property number 4, like poles repel and unlike poles attract. So this we have learned in static electricity, where we talk about like charges repel and unlike charges attract. So please use the correct term. When we are talking about magnets, we use poles. When we are talking about electric charges, we use charges. Okay, but it's still the same thing. Like, something that's alike will repel, something that's unlike will attract. Okay, the next statement is very important. The only test to see if the objects are magnets is repulsion between the objects. So what do we mean by that? Okay, so this is the step to determine if an object is a magnet. So we move a magnet near the object. The object, I don't know whether is it a magnet or a magnetic material. Okay, so if the magnet is not attracted to it, then it is confirmed a non-magnetic material. That means it's not made of iron, steel, cobalt, or nickel. Okay, if it's attracted to it, it can either be a magnetic material or a magnet. So attraction can't tell us whether something is a magnet or a magnetic material. Okay, now if the magnet is repelled by the object, okay, that means the object now experiences repulsion. So example, I have a North Pole here and a South Pole here. This is my magnet, okay, and this is my object. Okay, if it experiences attraction, we cannot be 100%. We cannot even know whether if the object is a magnet or magnetic material. Okay, so what do we need to do? We will actually need to turn the object around. Okay, I turn it around. So example, here is A and here is B, and now B and A, they are facing the B is now facing the north, and if it still attracts, that means both A and side B are both attracted by the North Pole. Then it means that the object, it is a magnetic material. However, if it repels, right, just now N attracts A, but now N repels B, that means B must be a North Pole, because like poles repel, and therefore A must be a South Pole. So if A is a South Pole, that means there will be attraction. So that's why the only test to see if something is a magnet is repulsion. Okay, success criteria B, describe induced magnetism caused by placing magnetic materials close to a strong magnet or within a current carrying solenoid. Okay, so we have talked about induced charges in the chapter of static electricity, so it's the same thing. Okay, but the concept is that magnets are actually made of atoms. Okay, so at the subatomic level, the electrons circulate around the atomic nuclei and spin about their own axis. This movement gives rise to an atomic magnet. Okay, so the magnetic domain theory states that there are regions called domains in which the atomic magnets are aligned, and is used to explain why some materials are magnetized while others are not, because those non-magnetic materials do not have this magnetic domain. Okay, so the atomic magnet is represented by an arrow. The head of the arrow represents the north pole and the tail represents the south. So I can say that for this arrow, the north is at the tip, the south is at the end. Okay, so this is actually a domain, but in the other domain, the north is here, south is here. So they are actually the net magnetic force, right? The net magnetic effect is 0, okay, because they all have different orientations. So I have north here, south here, I have north here, south here, right? They sort of cancel each other out, okay? But when a magnet is brought near, okay, let's say this is south pole, and remember the arrows, they are the north pole, they will automatically be aligned, right, by induced magnetism to point towards the south pole. Okay, they will not be repelled, they are actually attracted to it, and therefore this will then be the south pole, and this will be south, and the north of the other domain will also then point to the south. They are attracted by it, and in the end I will have a collective north pole here and a collective south pole, and therefore attraction occurs as unlike poles attract. Okay, so it's written here, within the magnet, north poles are facing the south pole of other tiny magnets and vice versa. Therefore, the magnetic effect cancels each other, right? But at the poles of the tiny magnets are not being cancelled, and therefore the magnetic strengths are strongest at the poles here, right? The north and the south. Okay, so therefore north and south pole always occurs in pairs, right? And when the magnet is divided into two smaller pieces, right? Let's say two smaller pieces, then this will be north and south, right? Here will then be south and north, right? But if I join them together, then it will be one big magnet by itself. Okay, now when two bar magnets are joined together, the overall strength of the combined magnet is stronger than that of one bar magnet, of course, and is weaker than the sum of the strength of both magnets. Okay, that means if I have two magnets, north and south, and then I join them together, right, the total strength, right, will be weaker than the sum of the strength of both magnets. Okay, but the total strength will still be stronger than that of one bar magnet. Okay, so it will not be more than the it will not be equal to the sum of the strength of the magnet or larger than that. Okay, so induced magnetism can take place when a magnetic material is in contact or in close proximity, okay, or within a current carrying solenoid. So this current carrying solenoid will actually bring us to the next chapter called electromagnetism. So now I'll just do a very quick introduction. Okay, so we can actually magnetize magnetic material, which means to turn them into magnets itself. Okay, so this is what we call induced magnetism. Okay, so the first way is stroking. Now I have this permanent magnet, right, and I have a steel bar, which is a magnetic material. Okay, so the steel itself is not a magnet yet, so I need to stroke it. So notice the path of the magnet. The north actually comes in here, right, and leaves over here. Okay, so we need to stroke it with the north always coming in and leaving, or if I can also use a south, I can use the south pole and the north here. So if I go in with a south pole, right? I cannot midway switch the orientation of the magnet. I still need to stick to a south and the south pole touching it, right? And leaving the unmagnetized material. Okay, so if I have a south coming in, so then this part will be a south. Because think about it, if you want to make something into a magnet, if you want to make something into a magnet, you actually need energy, right? You need to sort of convert it into a magnet. So the moment I bring in my south, okay, there will be repulsion. There will be something that is resistive to it. So I need to put in some strength. And when I'm leaving, okay, this end becomes a north pole, becomes an induced north pole. Why? Again, I'm trying to stop the south from leaving. So the south is coming in, I resist it. The south is leaving, I also resist it by attracting it. Okay, and I do this many times. So in the end, this part will gradually becomes a stronger south, and this will be a stronger north, right? So if I want to make it even stronger, I need to stroke it more times, and that will use up energy from me. Okay, because you can't just change something into a magnet, right? So you have to use energy. This is in accordance to the principle of conservation of energy. Okay, so this is a popular kind of MCQ question whereby you can either change the direction of the stroking. That means south goes in from here, okay, and leaves here, or you can change the orientation of the magnet. So that's why MCQ 4 choices. You can either change the direction. You can either change the direction of stroking or change the orientation of the magnet. Okay. So the other one that is easier because we are going to use current. Okay, is the electrical method. Okay. So what is a solenoid? A solenoid is actually a coil of wire. It can be copper. Okay. But copper is not a magnetic material. Okay, it's not a magnetic material. It's just that the current, okay, will flow in this copper wire. The current will flow in the copper wire. Okay, so because copper is a good conductor, but it is, I stress that it is not a magnetic material, so the current will flow. So the thing about this is that when current flows, it will produce a magnetic field. Okay, when current flows, it will produce a magnetic field. Okay, just watch what I'm doing. I am actually drawing the direction of the current, right, on the outer facing part of the coil. Outer facing part. Okay, outer facing part of the coil, and I need y'all to be able to draw this current direction if it is not provided in the question. Okay, so maybe I can draw the solenoid being wound on a wooden stick. Okay, maybe I wind it on a wooden stick for support. Okay, now because of the wooden stick or the wooden rod, you are not able to see the coil behind. You are not able to see the part of the coil that is behind the wooden stick, right? Which I show using the dotted lines. Yes, so what you are seeing is only the front part, of the coil of wire, and this is good enough. Okay, this is good enough. I need you to be able to draw the direction of the current in the front part of the coil. What do I mean? So if I have a current that is flowing this way, right, current goes in this way. So if I were to be able to trace it, right, this front part of the coil will have the current flowing down this way. Okay, trace it. This part goes behind, and then I need to have this. Okay, so this part is very important. You need to have this. Sometimes O level, they are good. They are kind enough. They will draw all this current for you. Okay, so this is electromagnetism. When current flows, okay, it produces a magnetic field. Okay, so this is what you need to know. So besides magnet producing magnetic field, having a magnetic field, a current when it flows, it will also produce a magnetic field. Okay, so this is the relationship of electromagnetism. Okay, so what is important now is that if you look at the stroking part, they will ask you on what are the poles that will be produced on each end of the steel bar. Okay, for us, we need to be able to know what is the pole that is produced or induced on the end. So now if we were to switch to a iron rod, okay, if we switch to an iron rod inside here, right, we have current flowing this way. It goes to the back, right, which I'm not interested in. I'm interested in only the front part of the coil that is visible. Okay, so you need to draw the current's direction. Okay, so now how did this become a north pole? Okay, so you have to use this right hand grip rule for solenoid. Okay, later on I will introduce right hand grip rule for straight wire. Okay, it's still the same way of gripping. So imagine you are using your right hand, okay, and you are gripping something, right? This is your right hand, and your thumb points in this direction. Yes? Okay, so what does the finger represent? The fingers represent direction of current in the coil. Okay, so with this direction of this current, I need to grip iron rod. I need to grip an object between here so that it looks like this. So it is downwards facing. It is downward facing. Okay, and my thumb will be pointing to the right. So this right side will then be a north pole, and this left side will be a south pole. So this is how you use your right hand grip rule. That is why over here it is a north, and over here there's a south. Okay, now how about in this case? So again, we are using right hand grip rule, but in this case, the current is going up this way, current is coming down. But this is not important. I need all this. This part is the important part. If you were to trace the direction of the current, okay, and in this case, the direction of the current of the front part of the coil that's facing us is visible to us, we see that the current is going upwards. But there's no way that I can grip the rod using my right hand, okay, because the direction of the current is represented by the fingers, but now it is facing up, so I need to grip it the other way, and therefore my thumb will be pointing in this direction, right? So you can try it out. Use a pen, you grip it, and you must have the fingers pointing upwards. So there's only this one way that you can do it, and therefore the left hand side is a north and the right hand side is a south. So again, this is a very popular MCQ question, so it depends on the direction of current and also on the how it is coiled, how the coil is coiled. Okay, I can show you another example whereby I have current going down and current going up, exactly like this. Okay, but depending on the how the coil is being coiled, okay, okay, so as you can see, even though the current is in the same direction as this case, right, on the left hand side current is going down, on the right hand side current is going up, but if I were to trace it and if I draw the very important direction of the current on the front part of the coil, now my current is actually facing downwards. So I will then need to use my right hand grip rule, and therefore my north will be here. Okay, you need to practice this, but once you get the hang of it, it is very simple. Okay, so these are the two ways of magnetizing magnetic materials, stroking, and using direct current in a solenoid. Okay, so they are both very popular MCQ questions. So if there's magnetizing, there's also demagnetizing, right? It can be achieved by causing the atomic magnets to point in random direction. So heating, when heated, the atomic magnets vibrate vigorously and they will therefore lose their alignment, okay? So leaving the magnet to cool in the east-west direction will ensure that the magnets do not realign. But why do we need to leave it in the east-west direction? Because the Earth is a magnet. So if I were to leave the magnets, so this is north, south, west, and east, okay? So if I leave it in the east-west direction, then they will not be subjected to the Earth's magnetic field and they will not realign again. Okay, so I should put it this way and not this way. If not, then they will realign. Okay. Next is heating or hammering. Hammering a magnet in the east-west direction alters the alignment, right? Again in the east-west direction and causes it to lose its magnetism. Okay. Then just now the second method for magnetizing is using electrical method. We can also use electrical method, okay, but this time we are using an alternating current. What is alternating current? AC. It means that the direction of the current keeps changing. So the alternating current in Singapore is about 50 hertz. That means current changes direction 50 times a second. Okay, so every time it changes direction, the magnetic domains will change direction as well. So in the end, the alignment of all the magnetic domains will be disrupted, will all be misaligned. Okay, and besides putting it in the solenoid where the AC current is flowing, we need to withdraw the magnet from the solenoid in the east-west direction. Again, same thing as this. Okay, and we need to do this a few times. So this results in the atomic magnets being misaligned and pointing in random directions. So during O level, sometimes they'll ask this question: how describe a way or experiment on how to demagnetize a magnet. So I would always prefer this because then I can draw a diagram to support it. So if it's 2 marks, I draw this diagram and I write a few lines. What are the steps? I will surely get the marks. Okay, whereas hitting and hammering may not usually hit the point, so I will use this. Or sometimes O level they will specify by using electrical method. Okay, describe how you would demagnetize a magnet. So they will force you to learn this. Okay, so it's good to learn this. Okay, storing magnets when subjected to long periods of heat or influence of nearby magnetic fields, magnets can become demagnetized. So to prevent magnets from being demagnetized, iron keepers, okay, iron is a magnetic material. They are used to reduce stray magnetic fields and to prevent unwanted magnetized material from being attracted to it. So because these are made of iron, okay, and iron is a magnetic material, and remember the field lines go from north and enters the south, which means that this part will be south and this part will be north. Therefore, the magnetic field lines will be kept within this system. It will be kept within this system. So there will be no stray magnetic field lines going outside. So this is a way to keep the magnets, the magnetic field strong for a long period of time. Okay, success criteria C, distinguish between temporary magnets, iron, and permanent magnets. So there you have it. This is the difference between iron and steel. Steel can be used to make permanent magnet. Iron can be used to make temporary magnet. Okay. So magnets are temporary or permanent depending on the materials they are made of. Temporary magnets are magnets that retain their magnetism in the presence of an electric current or a permanent magnetic field. They can retain as long as I have electric current or permanent magnetic field around it. Okay, but permanent magnets do not require electric current or permanent magnetic field to retain, right? So we can break it up into two types: permanent and temporary. Temporary need a electric current or permanent magnetic field around. Okay, so permanent magnets are made of hard magnetic material. Temporary is made of soft. Okay, hard and soft doesn't mean the texture or how it feels. Okay, it refers to the material's ability to become and remain magnetized. So the soft one is your iron. Okay, hard is the steel. So for iron, it is soft magnetic material. It is easily magnetized and demagnetized. I'm sure you have some friends who like they are very easily persuaded by you. You ask them to go and watch a movie, ask them to go and eat lunch or dinner, they'll just readily say okay. But even when you say, maybe don't cancel lunch, cancel the movie date, they are also okay. So these are people that are soft, something like that. They are easily magnetized and demagnetized. They are easily influenced. But there are also friends that are very hard to persuade. They are very difficult to magnetize and demagnetize. Right? Imagine you want to ask your friend, okay, who is very hard to influence, to go for lunch or dinner. You'll need maybe a few hours to persuade them. Okay, then after that they will agree. Okay, then imagine now you're unable to go for the movie or for lunch or dinner, and you say you want to cancel it. They will say no. They will die still want to go and eat with you or watch a movie with you, because they are very difficult to demagnetize. Okay, so something like that. So what is the uses of soft iron? They can be used to make temporary magnets, such as electromagnets in junkyards. Okay, so junkyards, they have this electromagnet. They supply a current to this soft iron. Okay, and it is able to lift up the cars. Okay, lift up cars. When the current is switched on, they very quickly becomes a magnet. Okay, so once this car is transported to the required location, by just turning off the current, this thing stop becoming a magnet and the car will just drop down. Okay, so that is how iron is being used as a temporary magnet. I just need it instantaneously, and when I don't want it, it can stop being a magnet. Okay, but for steel, it is hard to magnetize and hard to demagnetize. So example, your fridge door, okay, they are hard magnetic materials. They can be used to make permanent magnet. Therefore, even when there's no current or no magnetic field around it, it will still remain as a permanent magnet. So that's why you can close and open and close the door of the fridge. Okay, so soft magnetic materials have stronger induced magnetism compared to hard magnetic material, right? Because they are very easily magnetized. So at the start, once I have a similar magnets and both are becoming induced magnets, the iron will tend to have a stronger magnetic field because they are easily magnetized, right? Whereas for steel, they can still be magnetized, but their strength is not that strong. Okay. However, once I remove the magnets, all the pins will drop, all the paper clips will drop from the iron because they don't retain their magnetism. But once I remove the magnet for steel, there will still be some of the paper clips being attracted to it, because the steel retains magnetism. Okay, they are harder to demagnetize. Okay. Success criteria D, describe how a bar magnet can be used to determine the direction of a magnetic field. So magnetic field is the region surrounding a magnet in which a body of magnetic material experiences a magnetic force. So this is our definition of magnetic field. We have also done electric field. Okay, what is electric field? It's the region surrounding a charge, okay, in which is the region whereby a charge, okay, experiences a electrical force. Okay, then we also have gravitational field. So it's the region whereby a mass experiences a gravitational force. So we actually have three kinds of fields. 1, gravitational, 2, electric, and 3 is your magnetic, right? We have 3 kinds of field. By just changing the body, magnetic material, or changing into mass, or changing into charge, and then talking about what kind of force, we can have all three definitions. So you don't need to memorize all three definitions. Okay? Okay. Magnetic field strength of a magnet is strongest at its pole. If the iron filings are sprinkled around a bar magnet, the iron filings will fall into lines. So it will look like this. Okay? But we also need to know how to draw the field lines. The field lines are closely packed at either poles of the magnet, but are more spaced out on both sides as well as further away from the magnets. See, very closely packed, and they are spaced out further away. Okay, they also connect the opposite sides of the poles and are present within the magnet. So within the magnets, there are also field lines, but it is not visible. But you see, it will just continue like that. They'll just continue like that. Okay, so even in a solenoid example, if I have a current, okay, and let's say this is the north pole, this is the south pole, right? So the field lines will be coming out this way, comes up from north, enters the south, but within the coil itself, it will be a closed loop. Okay, north, comes up from north, flows out, and enters the south. Okay, so you must also know how to draw within the magnet or within the solenoid as well. Okay. Okay, so take note, magnetic field lines are directed outwards from the north pole and into south pole. Okay, so it's like your charges. So for positive charge, the field lines are coming out. For negative charge, the field lines are going in. Okay, are going in. Magnetic field lines do not intersect or cross one another. We have learned this in our electric field lines. Field lines are drawn closer to represent stronger fields and vice versa. We have also covered that in our static electricity. So if we have a uniform magnetic field, they will have lines that are equally spaced out. So this is like our electric field, whereby we have positive plates and negative plates, right? Then there will be uniform field lines within the plates. Then over here we'll have the ones that are pushed outwards, right? So a non-uniform magnetic field has field lines that are not equally spaced, and hence they are not parallel to one another. Okay, so at different points, the magnetic force exerted will be different. I would say because here the field lines are closer together, therefore we have a stronger magnetic field strength over here. But because over here they are more spaced out, so it is weaker. And it is understandable because the further away you are from the pole, the weaker the magnetic field strength. Okay, then E, draw the magnetic field pattern around a bar magnet and between the poles of two bar magnets. So O level sometimes will get you to draw. Okay, so the field lines can be used to represent interaction between two magnets. So it's not just within the magnet, one magnet, I can have two magnets. Okay, and unlike poles attract, take note, and when they are placed next to each other, the field lines go from the north pole of one magnet to the south pole. So as you can see from here. Now you do not need to use dotted line. You can use a bow line to draw. Make sure that the direction is correct. Make sure that the pattern is correct. So they are looking out for direction. So means coming out from north, entering the south. They are looking out for the pattern. Okay. So draw enough to show the pattern, right? And not excessive. Because the more you draw, sometimes the direction you will tend to miss out one or two and it becomes wrong. Okay, and because light poles repel, when two light poles are placed next to each other, the field lines move away from each other, because remember, the field lines cannot touch or cross each other. So if I have two north, then it will look like this. Okay, they cannot touch. So this point X is called a neutral point because the resultant magnetic field in that region is zero, provided that both magnets are of equal strength, right? Examples of magnetic field lines where the magnets are placed side by side, it looks like this. Okay, so you may need to learn how to draw this. Okay, so now draw the magnetic field lines between the pairs of magnets and indicate the direction that the compass needle points in. So this is north, so the field lines will go this way, right? Okay, because they cannot, the field lines cannot touch each other, right? And so take note of the direction. Okay, so the field lines do not touch each other, and the direction is coming out from the north. There will be some that enters the south, like that, and south this way. Okay, you can repeat for this side as well. Okay, then, so this is how the field lines look like. Nothing different from this example, yes? Okay, then they ask you, what will the direction of the compass point in? The compass needle points in the direction of the field lines. Okay, so this is important. It's not explicitly written in your notes, but please copy this down. The compass needle points in the direction of the field lines. So we see that the field lines is going in this way and my compass is there. So the compass will point in the direction of the field lines. So now if I have a compass here, what direction should it point? It will be pointing in the direction of the field lines that is nearest to it and which affects it. Okay, so if I have a compass here, a compass needle here, okay, it will be pointing this way. If I have a compass here, it will be pointing something like that, this way. Okay? So again, this is a very popular kind of MCQ question. Okay, so this is the summary. Yep. And that will be the end for this chapter.